Welcome to Math 63. This is Unit 2, Lecture 1, Basic Algebra. First part, background into algebra. The year is 1820. The place, Baghdad, capital of the Abbasid Caliphate. Muhammad ibn Musa al-Khwarizmi has been appointed by Caliph al-Ma'mun to be the astronomer and the head of the library of the House of Wisdom, the great academy of the Abbasidian Empire. The Caliph has also commissioned a book, Hisab al-Jabr wal Muqabala, the compendious book on calculation by completion and balancing. I apologize for my butchering of Arabic there. This book would be translated and live on to become the principal math textbook at the universities of Europe for centuries. It also would give part of its Arabic name, Algebra, or algebra, to the branch of mathematics it covered. In this book, al-Khwarizmi showed how to solve any linear or quadratic equation. He did it using only the mathematical tools available at the time. Using letters to represent unknown quantities was unheard of in the 9th century, so his style is, well, it's a little clunky. Here's an example from an 1831 English translation. If you can follow this on first hearing, you are a better person than I. 2 squares and 10 roots are equal to 48 dirhams. That is to say, what must be the amount of 2 squares which, when summed up and added to 10 times the root of one of them, make up a sum of 48 dirhams? You must at first reduce the 2 squares to 1, and you know that 1 square of the 2 is the moiety of both. Then reduce everything mentioned in the statement to its half, and it will be the same as if the question had been, a square and 5 roots of the same are equal to 24 dirhams. Or, what must be the amount of a square which, when added to 5 times its root, is equal to 24 dirhams? It goes on, but I hope you get the point. Algebra was way more difficult to follow back in the Middle Ages. The algebra presented a long list of recipes for dealing with various equations. Recipes that are used to solve problems are now called algorithms, after the man himself, al-Khwarizmi. All of al-Khwarizmi's algorithms relied on geometric proofs. This was because geometry, starting with Euclid's textbook Elements, was considered the foundation of all mathematics. Humanity would have to wait centuries before someone came along to put algebra on an equal footing with geometry. First, though, we needed some things to speed up the process. We needed better symbols. As time went on, mathematicians started getting tired of writing the same words over and over, like add, subtract, or is equal to. In Europe, the Hindu-Arabic numeral system had finally taken over from Roman numerals, and people were starting to invent new symbols of their own. In 1518, German mathematician Henricus Grimatius used a cross and a line to represent plus and minus. In 1557, Robert Record of Wales used both of these in his book The Whetstone of Wit. In the same book, he debuted the equal sign. Howbeit, for easy alteration of equations, I will propound a few examples, because the extraction of their roots may the more aptly be wrought. And to avoid the tedious repetition of these words, is equal to, I will set, as I do often in work use, a pair of parallels, or gemwoe lines, of one length, thus the equal sign, because no two things can be more equal. By the way, gemwoe, or maybe jimwo, Jumeaux, that's probably it, is French for twins, so it's twin lines is what he's saying there. All right, a few decades later in France, François Viète developed the theory of algebra that was no longer chained down by the difficulties of common language. He began to use letters to represent unknowns and was able to create an axiomatic system of algebra that was as nice and neat as the one Euclid had created for geometry 18 centuries earlier. Viète's system was not the final iteration, however. He hadn't used Ricord's equal sign, and he made the strange decision to use vowels to represent his variables and consonants for the coefficients. It would fall to the great philosopher and mathematician René Descartes to perfect Viète's system. From him, we get the tradition of using the last letters of the alphabet for variables, starting with x, and the first letters for coefficients. He created the modern notation we use for exponents, which we will cover later in this lecture. Also, he is considered the father of analytic geometry for developing a system of coordinates that we now know as the Cartesian plane. We'll talk more about that development in Unit 3.